Hey everybody, happy Friday. Good to see ya. Let's pick up where we left off yesterday, okay? Nothing really to talk about. Eventually here, we'll get enough of 2.7 covered where you can start working on homework topic 3. I'm not going to make homework topic 3 due until next week, Wednesday at midnight. So you're going to have plenty of time, and there's still certainly more we can teach and get you further on this note sheet. But the bulk of topic 3 is going to be on this early part of 2.7, these molecular geometries. So yesterday, I introduced this and we started filling out that big giant grid, which is on the back side of the first page of 2.7, and we'd only done the first 3 examples. So just a couple things that I want to point out as we kind of move forward. One of the first things I want to point out is the coordination number, okay? So the very first column on this grid is, and it obviously looks like this, it should be in front of you at the moment, but the very first column here is the coordination number. And the coordination number is the number of items that are trying to be separated in 3-dimensional space, okay? So those are either going to be atoms or lone pairs. And when we count them, we're counting around the central atom. So in this first one of the beryllium fluoride from yesterday, the coordination number was 2. Here's my central atom. How many things are separating, or how many things are we attempting to separate around the central atom? 2 things. 1 fluorine, 2 fluorines. Okay. In the next one, the coordination number is 3. Why is it 3? Because here's my central atom, boron, and I'm separating 3 chlorines from around that. In the third one, tin 2 chloride, the coordination number is 3 because it's not just atoms that matter, it's also the lone pairs on the central atom, okay? So tin is in the middle, 2 atoms, 1 lone pair on the tin. We are separating 3 things in 3-dimensional space. That's what VSEPR theory is trying to talk about, okay? The VSEPR theory is describing that when you have atoms or bonding electrons, like these bonds, the dashes, right? And when you have lone pairs of electrons, these electrons repel. The electrons in this bond right here, the electrons in that bond right there, and the electrons in this lone pair up top all are repelling one another, and they're pushing each other away as far away from one another as they can get in 3-dimensional space, okay? Yesterday, we added no depth. The first 3 molecules we looked at were linear, trigonal planar, and bend. All 3 of those are in a plane. They are in the XY plane. They have no depth whatsoever. We're going to break that right now, okay? So for our 4th example, we have carbon tetrabromide. Same as always, let's do a Lewis diagram first. And again, I would encourage you to pause it and try these by yourself because I think you can do it. I really do. But if you want to just watch, that's fine too. Okay, so actually, let me say this. I'm sorry. Before you start drawing the Lewis diagram, you're going to want to leave some space. If you can write really small, awesome. You can kind of like split this box down the middle because we're going to have like 2 pictures that matter. We have the Lewis diagram picture, and then I'm going to try to draw the molecular geometry, the 3-dimensional picture of this molecule. Again, I kind of forewarned you yesterday it's not going to look very good, but I'm going to try, and then we'll jump over to that Illinois website, the Chem Illinois website, to check out those 3D models. Okay. Sorry about that. Little technical difficulty. So let's try this carbon tetrabromide one. Okay, let's draw out our Lewis diagram. And again, try to leave space so we can draw a 3-dimensional picture and a Lewis diagram. It's going to be tight, but anyway. All right. So carbon tetrabromide, CBr4. Total valence electrons to work with is bromine each has 7, 28, plus another 4 is 32. Carbons in the middle. Bromines are on the outside. This took 8 electrons. I still have 24 to go. I can add those on all of the bromines. Leaving me with none. Formal charges are all 0. This is my structure. Now, I'm going to try to draw a 3D model. Let me explain what my little symbols mean, because I'm using kind of some symbology to help try to show depth, because again, I'm not a good artist, and this is a pretty standard way of attempting to draw these things. Carbon's in the middle. The bromine that's upward, I'm going to put in my plane, meaning like here's my board or here's my paper if I were working on a desk with a piece of paper. These two are in the XY plane. I'm not showing any depth with those two atoms. This bromine over here, I'm going to draw kind of at an angle and leave that in the plane as well. In other words, these 3 atoms are all in the same plane as my paper or my whiteboard or smartboard. The other 2 atoms are going to have depth. They're going to be out of this plane. So I'm going to use a dash and a wedge to kind of assist with some depth. All right? So a wedge is showing an atom coming out towards you. Okay? And a dashed line is showing an atom going into the whiteboard away from you. Now, I have a hunch you cannot visualize what the heck that's supposed to look like at the moment. So let's go to the Illinois website and find it. Okay, so we have the ones from up above that we showed yesterday, the linear one, the trigonoplanar one. Hey, here's the bent one. And again, just for the sake of argument, we didn't show this yesterday. You can rotate it, right? And it's bent. And if I flip it on its side, hey, look, all 3 of these atoms are in the plane, right? So it is a flat molecule or a planar molecule. If I go down further, we're going to reach what we are at right now. Now, this is called tetrahedral, which you can see right over here. Okay, I'll write that on our presentation in just a second. But let me kind of orient this the way that I have drawn it. Okay, the way I've drawn it on my smartboard is like this. I have the central atom, the upward facing atom, and the left facing atom all in the plane. In other words, if I flip it like this, right, you can see that all 3 of these atoms are in the same plane. So let me flip it back, and I have drawn a wedge to represent this one, which is coming out towards you, and I have drawn a dash to represent this bond to that atom that's going in the board away from you. Okay? So this is what I'm attempting to draw, and yes, very clearly it's not great, but I'm hopeful that this website is kind of clarifying what I'm trying to do. Okay? Now, a couple other things. This tetrahedral shape is really, really cool because it has perfect symmetry. Let me show you. It looks like a little tripod, right? Do you see that? How like the 3 bottom atoms kind of bow out and downward just a little bit, and then there's one straight up and down. But every single one of these bonds, or the angles, I'm sorry, every single one of these angles between these bonds is the exact same. They are all 109.5 degrees. If I take this atom and make this one my upward facing atom, look at that. It's the exact same shape. If I take this one and make that my upward facing atom, same shape. How about this one? Same shape. This thing has perfect symmetry. It's kind of tough to see it at first, but every single angle between these atoms, if you pick any 3 atoms and make an angle, it's 109.5 any which way. And you can take any one of these 4, orient it as your top one, and you still end up with this exact same shape, this little tripod with an atom straight up and down. Okay? So let's go back. This is called tetrahedral. Let's write that down. I apologize for my flickering camera on the whiteboard. Obviously, it's on your video, it's not flickering, but for whatever reason, the program I'm using is freaking out on me, as it has a couple times in the past. But anyway, so that's called tetrahedral. The angles here are 109.5 degrees. Yes, it is that specific. And yes, if you look up VSEPR theory and molecular geometry anywhere, they will all report this or record this as 109.5. So It is what it is. Take that 4 sig fig number and use it every single time if you're asked for this angle, okay? So this is our first molecule with a coordination number of 4. In this case, it's 4 atoms, right? Here's the central atom carbon. We are separating these 4 atoms in 3-dimensional space around the carbon. And they repel as far as they can, and that repulsion leads to this geometry or this shape. The 4 atoms are all separated by 109.5 degree angles, and we call this shape tetrahedral. All right, next one, ammonia. Ammonia has a formula of NH3. Total valence electrons to work with, we have 8. Nitrogen has 5, each hydrogen is 1. Nitrogen is going to go in the middle. And we have 1 hydrogen, 2 hydrogens, 3 hydrogens, and I'm kind of drawing it like this on purpose. Okay, I did not make a triangle. Again, I'll kind of get into why. That took 6 electrons. I have 2 left to add. They aren't going to go on hydrogen. Hydrogen can't take any more. So they're going to have to go on nitrogen. Okay. All of our electrons are added. You can check formal charge if you'd like. Hydrogen, 1 valence electron, minus 1 dash. It's 0. We're good. Nitrogen, 5 valence electrons, minus 1, 2, 3 dashes, 1, 2 dots for 5. Formal charge is 0. We're good. This is the correct structure. Now, let me attempt to draw this 3-dimensionally. The way this is going to look 3-dimensionally is, there's my nitrogen. Here is a hydrogen. And then these other 2 are going to have depth. Okay? And up above, I would have the lone pair. I'm not going to draw that in because I don't care about that when I'm describing the shape. Okay? The molecular geometry gives us the shape name. So let's go to the website. Let's look at this. If I scroll down a little bit, here we are. And you can see they drew their Lewis diagram just a little bit differently, but in a Lewis diagram, the angles don't matter. Okay? We're not trying to show perfect geometry or the appropriate angles in a Lewis diagram. We're just showing where the electrons are. If we want to look at the angles or care about the angles, we draw a 3D model. So here's what I have. Okay? What I've really done, if you compare these two, okay, here was my tetrahedral shape, 4 atoms, coordination number of 4, which is said right there. 4 atoms, they're all pushing on each other and they separate like this. In this example, I have 3 atoms, but I still have a 4th lone pair, or a lone pair there, right? So the coordination number is still 4. And as a result, I end up with a similar shape, almost the exact same shape, right? That 4th atom from that previous example would be up top right here, straight up and down. But instead of having a 4th atom, what I have is a lone pair. And as a result, I get the similar shape, but it's kind of like I've just removed this atom up top. I've taken that away, and I've replaced it with a lone pair, which we don't really care about in terms of describing the molecular geometry, right? We don't account for the lone pair in describing the shape. We only account for the atoms. So here's how I've drawn it, right? I have these 2 atoms in the plane, the central nitrogen and the outer hydrogen. And the other 2 hydrogens I'm showing having depth. This is my wedge coming forward, and this one would be my dash going backwards. Now, the angles here, look at this. It says 107. I'll talk about that in just a little bit. The shape name is a trigonal pyramid. Okay? Trigonal pyramid. That is the shape name. This says tetrahedral over here because this is the electron geometry. If you remember those 2 terms that we defined yesterday, okay? The geometry of the electrons around the nitrogen is tetrahedral. We're separating 4 things. It's a coordination number of 4. But the geometry of the molecule, or just the atoms, is trigonal pyramid. Now, why is it trigonal pyramid? Well, there's 3 things. And hey, look, it's not flat, right? It's bowed downward. These are all having a slight downward angle because of that lone pair up above. So we call this a trigonal pyramid. Not to be confused with this guy that we learned yesterday, which is trigonal planar. This is flat. This is in the plane, right? So we have trigonal planar, and we also have a trigonal pyramid. All right, so let's finish up our notes on that example. So, yeah, trigonal pyramid is the name. And the angle is 107 is what they had there. Now, I'm not even going to go there because here's why. AP will accept an answer of 109.5. But let me be a smidge more specific, okay? I'm going to call this less than 109.5. Here's what's going on. It's a coordination number of 4. We are separating 4 things around the nitrogen. 3 atoms, 1 lone pair. Those 4 things repel as much as they can and separate as far as they can. But lone pairs of electrons actually have slightly greater repulsion than bonding pairs of electrons. Let me explain that. If I did draw in my lone pair over here, you don't have to do this on your sheet if you don't want to. But if I did, that lone pair would be straight up and down. This lone pair has just a little bit stronger repulsive forces towards the 3 atoms of hydrogen. And as a result, it pushes just ever so slightly downward on those hydrogen atoms. And as a result, this angle here between these 2 hydrogens is just ever so slightly less than the 109.5 that we would expect for a coordination number of 4. Okay? The good news, like I had said just a little bit ago, AP will accept a range of angles. What I mean by that is, when they've asked a question like this on the AP test before, they literally will accept anything from 104 to 110. Okay? So if I only teach you that this is 109.5, you're actually okay. You can write 109.5 for the angle of this bond on an AP test, and you would absolutely receive credit. But it's I figured we're here, right? We can learn that that lone pair is a little more repulsive, or it has a slightly stronger repulsion force, and as a result, these angles just get pinched just a tiny baby little bit. Okay, so we'll call this less than 109.5 for that angle. All right, next one. Let's go to water. So we're very familiar with water, but we've never actually looked at the 3D geometry of that molecule, right? So let's go through the motions. Let's do exactly what we've been doing. Let's do a Lewis diagram to start with. We know the formula is H2O. That's nice and easy. How many valence electrons do we have to work with? Hydrogen has 1. Oxygen has 6. So we've got 1 from the 2 hydrogens, 6 more from the oxygen. We've got a total of 8. We're going to put oxygen in the middle. Now, that's a little funky because we've been putting that first atom in the formula in the center almost always, right? But remember, hydrogen can only form 1 bond. So we can't put hydrogen in the middle. That doesn't make any sense. It can only make 1 bond to one other atom. So we couldn't possibly attach 2 things to it. So oxygen's in the middle. I'm going to draw this downward and have my hydrogens down like that. But here, we've used 4 electrons. I'm sorry, I'm getting ahead of myself. Let me finish my model. I've got 4 electrons to go. I can't add these to the hydrogens. Hydrogen just wants the 1 bond and nothing else. So I'm going to add these 4 electrons as 2 pairs on my oxygen. And I've got nothing left. Now, this looks very similar to a shape we've already made. And we're not going to name it differently. This is bent. It is, right? I mean, if you look at the atoms, we have a hydrogen, an oxygen, and a hydrogen, and it's bent. It's not linear, right? However we want to say that. The angle of this one, however, is slightly different because the coordination number is different. This is still a coordination number of 4. We have 2 atoms. We have 2 lone pairs. We are trying to separate 4 things around that central atom of oxygen. So the generic shape, or the electron geometry of this molecule, it would start as this tetrahedral arrangement. Okay? Water, or the lone pairs and the atoms in water around the oxygen, will make this shape. Okay? And essentially, and I'll go to the website now, we end up with a bent molecule, right? So here's my bent molecule. Okay, there's the water. Now, what they don't show you, okay, and this is linear, or sorry, planar, I should say, I'm sorry. This is planar. But what they don't show you is where these lone pairs are. Okay, so let me go back up to the tetrahedral one and kind of explain what's happening here. So if I turn this, if I can, oh, come on, don't fight me. There we go. If I turn it like this, okay, this is oxygen, this is hydrogen, this is hydrogen. It is a bent molecule. But what I've done with those two lone pairs is I have replaced the two upper atoms in this orientation with lone pairs. This would be a lone pair. This would be a lone pair. So I'm not going to draw a three-dimensional version of where those lone pairs should go, but it's still coordination number 4. I'm still separating 4 things in my water. It's 2 atoms, 2 lone pairs. The atoms, the hydrogen, oxygen, hydrogen, can all fit in the same plane. But if I put these all in the same plane, like the way I drew it for us on our presentation, the lone pairs are actually out of that plane. Okay, they have depth. So here's my water molecule right there, all in the nice same plane of my paper or my smartboard, but the lone pairs would be upward and towards you and upward and away from you into the smartboard, if you can kind of see that depth, right? So again, still coordination number 4, but the depth we use for these lone pairs, and to describe the shape, we just would only describe the shape of the atoms, which is bent. Now, if I scroll down and I look at the angle, you'll see that they have 104.5, okay? For the same reason as what I just described on ammonia. Let's go back to the smartboard here and finish this up. I'm not going to write 104.5. I'm going to write that this is less than 109.5. Because if you wrote 109.5 on an AP test, you're going to get credit. So don't overthink it. But we're here, let's talk about it for just a second. We have 2 lone pairs. And lone pairs of electrons have a greater repulsion than atoms or bonding pairs of electrons do. So these 2 lone pairs are both repelling on this bond in the water more, right? So this angle down there is getting pushed or pinched downward just a tiny bit, and it makes it less than 109.5. So in ammonia, we had 1 lone pair, and that has a greater repulsion, and it was pushing all these hydrogens and pushing them downward just a little bit, and we get 107-ish, 107 degrees, give or take. In water, we have 2 lone pairs, and now both of these have greater repulsion, and they're both pushing just a little bit more on those hydrogens, and we get the bond squeezed even a little bit more tightly, and we end up with like a 104.5 according to that website. Again, that's all well and good. You're more than welcome to share or to store that little nugget of knowledge in your brain, but at the end of the day, if you're on an AP test, if you write 109.5 for anything, any of these 3 examples with a coordination number of 4, you're going to get it correct. 4 atoms, coordination number 4. 3 atoms, 1 lone pair. Coordination number is 4. 2 atoms, 2 lone pairs. Coordination number is 4. All right. Let's go through a couple. Maybe I'll do like the first 2. I don't want to make this video too long. I'm already pushing 24 minutes here. So let me do the first 2 for coordination number 5, and we'll pick this back up. I don't want to give you a ton on a Friday. I just don't. So phosphorus pentachloride. PCl5. Okay, total valence electrons, we have 7 times 5 for the chlorines is 35, plus another 5 from the phosphorus. We have 40 electrons to work with. Phosphorus is going to go in the middle, and I'm going to put my 5 chlorines around the outside. Now, again, this is my Lewis diagram. Lewis diagrams are not showing 3-dimensional depth. The point of a Lewis diagram is to not show, or it's not necessarily to show the actual shape or the geometry. We'll deal with that if I draw a 3D picture, okay? This Lewis diagram is simply to show where the electrons are. So we're going to ignore making this 3-dimensional in a Lewis diagram. That required 10 electrons to make those 5 bonds. I have 30 left. There we go. They're all gone. I got nothing. Check your formal charges. Hey, spoiler alert, they're all good. Okay? They're all good. They're all going to be 0. Now, this is the Lewis diagram let me draw the three-dimensional shape. And again, to the best of my artistic ability. I have a phosphorus in the middle. I'm going to have a chlorine up above in the plane of my paper or my smartboard. I'm going to have a chlorine down below, also in the plane of my paper. I'm going to have a chlorine off to the left in the plane. I have 4 atoms that I can orient along my paper plane or my smartboard plane. And again, when I'm using the word plane, I am talking about math, right? The XY plane of a coordinate system. The other 2 chlorines are going to have depth. They're going to be 3-dimensional, have some depth, either in or out. So I'm going to use a wedge to show that this chlorine is going outward towards us. I'm going to use a dashed line to show that this chlorine has inward depth going back into the board away from us. Okay, let's go to the website. All right. And by the way, if you saw that, I skipped that example. It's not a good example, and it's not worth teaching. So anyway, here they have the exact same molecule, which is kind of nice. This is the shape, okay? And let's see if I can zoom in just for fun. Just so you can see it a little better. There's the shape. Now, the way I have drawn it is like this. I have the central atom, the upper, lower, and left-facing atoms, the chlorines, all in the plane. So let me just flip this for a second. You see all these 4 atoms can all be in the same plane, right? If I slice that right through there, they're all in the same plane. So I've drawn it like this. These 4 atoms are in the plane, and then I've drawn the remaining 2 atoms outward and back in your system. So this was my wedge right there. This is my dash back there. Okay. Now, the shape name of this is called trigonal bipyramid. Okay? Let me explain. If you look down the center here, if I flip it like this, we have 3 atoms kind of around the equator, you could say, or equatorial. Okay? These 3 atoms are like the equator if we were talking about a globe, right? If I flip it on its head or flip it on its side here, you'll notice that these 3 atoms make a nice perfect triangle, hence trigonal. Bipyramid is talking about 2 pyramids. Well, where are the 2 pyramids? I got one going upward. If I if I put like a piece of paper over these 3 atoms, right, it would make a nice like flat surface. And if I put a piece of paper over these 3 atoms, it'd make a nice flat surface. And if I did it over here too, I'd have a nice pyramid going upward from those 3 equatorial atoms. And if I look at the bottom, I can do the same thing, right? So there's a pyramid up top with a triangle from the center 3 atoms, and there's a pyramid on the bottom with the triangle from the center 3 atoms, hence bipyramid. So a trigonal for the 3 atoms in the middle or on the equator of this shape, and bipyramid for a pyramid above and a pyramid below. Okay, kind of funky. Now, if you're looking at the bond angles, take a peek. We got everything. We got 90s. Where's a 90-degree angle? Right here. Right here. From any of the 3 atoms on the equator to the top, or any of the 3 atoms on the equator to the bottom, we have 90-degree angles. There they are, right there. If I flip it on its side, we see 120-degree angles. The 3 atoms along the center or on the equator, as I'm describing it, have 120 degrees between them. They make a nice perfect triangle. And if you hold on, let me flip this again. There we go. They also are all in the same plane, right? You see that? If I used like an XZ plane, okay, they're all in the same plane. So we've got 90s, we've got 120s. We also have 180. If I go from the top to the bottom, right, this angle right there, that's 180. We've got all sorts of angles on this thing. It's kind of a funky shape. It's kind of a cool shape. Okay, but let's write all that down. And I'm going to stop after this one, by the way. I'm hitting a half hour. That's enough. So let's write this down. We'll call it a day. Have a great weekend, and we'll pick it up next week, okay? Trigonal bipyramid. The angles We have 90s, we have 120s, and we have 180s. We got a whole bunch of everything. And again, it's just kind of the uniqueness of this shape. So this is our first example with a coordination number of 5. We got 3 more of these to take a peek at. We also have examples with coordination number 6, meaning separating 6 things that we'll have to look at as well. We'll pick that up Monday. Again, I don't want to keep plowing forward if we don't have to, so we're good. Let's call it there. Please have a great weekend. If you have any questions, reach out to me. I'll try my best to respond. I'm not overly responsive over the weekends because I have 2 small children that tend to take up my time, but that's a good thing. That's what I should be doing with my time. Anyway, see you guys later.